Okay. Last time I want to talk about capacitors. This is gonna be a shorter like section, right? Because capacitors are much more complicated topic. They're also not as big on the MCAT as like just circuits or electrostatics. So I'm gonna be just covering the basics. If you have any more like advanced capacitor questions, please come to office hours with like specific questions that you might have. Like Google is also good, but most like the capacitors themselves are already low yield, but out of the low yield topic, I'll be telling you what the highest yield stuff is from that low yield topic. So right, anything more specific to that is be very, very rare that you'll find on the test, right? So first we want to talk about what are capacitors. Capacitors are essentially two plates a certain distance from each other. So if you actually remember on a circuit diagram, they look like this. That's because that's what they look like in real life. It's this is like these are square like plates. This, if you have like a front view, is like a square plate, right? Like this, like think of your hands, right? If you like turn it this way, it looks like this, right? This is exactly what they look like. Capacitors, and they have a certain distance between them, d, right? Their exact function in a circuit is not very high yield, and it's a little bit complicated, and it would require like a lot more explaining, a lot more going into it, into like electrical fields and stuff. But there are some important equations that you should know regarding them. Firstly, they have units of farads or F. And somebody asked, there was microfarads, right? I believe the most common one you'll see is either microfarads or millifarads. Those are the most common scales for them. You don't really like 1 farad is like a huge capacitance. You don't ever really see that in a question because it's just a ridiculously big number, or it's just like a ridiculously big thing, right? Most capacitors have either milli or micro, right? The two important capacitor equations are these two. Q equals C over V, and C is capacitance, right? That's the measure of a capacitor, just like resistance is the measure of a resistor. Capacitance is the measure of a capacitor. Q, you know, is charge, and V is voltage. This is how you would maybe relate capacitance back to charge and voltage, right? Then there's also this equation, right? And this is how you actually find capacitance with a certain capacitor without knowing like the charge and the voltage and stuff like that. It's equal to epsilon 0. It's like this is like a specific number to the like the material you use, right? It's the permittivity of the specific capacitor. A is the overlapping area of the plate. So like I said, this is what they look like, right? If you got like a front view, so like this is like this. If you got like a front view like this, right? The area, like this area, the surface area of the square would be A, right? And as long as they're the same size, right? That's what A is, it's the area in meters squared. And D is the distance between the plates. So it's like this area, it's like this distance between them. That's how you find a that's how you find capacitance. Ways to increase the capacitance of a capacitor, make the plates bigger, right? More area, bigger capacitance, or decrease the distance between the plates. If you increase the distance, capacitance decreases, decrease the distance, capacitance increases, right? So these are the two equations that you should know regarding capacitance. And if you just know these equations, that's pretty much all you really have to know for capacitors. You don't really have to know what they are, how they function, all that. This is the main thing you have to know about capacitors, but I'll give you a couple of extra info on the next slide. The electric field, like I said, inside a capacitor is constant, right? We haven't talked about electrical field yet, but if you already know what that is, electric field is constant. The net force in the middle of a capacitor is 0 on anything like on a dipole or something that's inside, right? If you had like a positive or negative charge, the net force on it would be 0, the electrostatic force mainly. When capacitors are fully charged, no current passes through them at all, right? And I want to actually go back to this. right? We technically, like, if this was a resistor, we know how to do resistance in parallel. We could find the current running through all of these. We have V, we have what the resistance is. How would we do it if we had a capacitor in here as well, right? Well, if it said this capacitor is fully charged, what that means is no current actually passes through it, right? So what that means is all of, like, even though these are in parallel, these two are in parallel, you can think of it as only it passes through this way, right? You can think of it only pass through this way because the current here, I at say C, which is the capacitor, equals 0. If the I here is 0, that means I R plus IC equals I total, right? So I total is the total, IR is the current through the resistor, and IC is the current through the capacitor. We know that IC equals 0, so we can actually just get rid of it. And so the I total is just equal to the IR, the current going through the resistor, just going through this portion, right? And so you can just find the total resistance this way. Like, consider this just like a box, and you can just ignore this whole area, right? Capacitor in parallel, like current in series. Capacitors in parallel, if they're fully charged, you add them together. So if you had, like, for example, I'm gonna clear this. If you had, for example, another thing here, and this had a resistor, right? You would have to add all three of these resistors, right? Like normally, you'd add all three of these lanes, right? Because it's split 3 ways. But you'd still normally do that, except you just know that through this lane, it's 0. So you're essentially only like adding these 2 lanes for current in parallel, at least.